Okay, so welcome. I'm Dave Tuttle of the Energy Institute. This is the Energy Symposium for Tuesday, April 19th, 2022. Our discussion today is Confronting Climate Gridlock, Technologies to Unlock a Clean Energy Future with Dr. Daniel Cohan. And before I introduce him, let me talk about the last two of the semester's UT Energy Symposiums. Next week, we'll have a discussion on environmental justice, climate change, air pollution and decisions in the U.S. power sector, Dr. Inés Azevedo. And then a week after that, Chief Executive Officer of Sonova Energy International, John Berger, will be talking about accelerating the energy transition. Meanwhile, let me introduce our distinguished speaker today. He is Dr. Daniel Cohan, an associate professor of civil and environmental engineering at Rice University. He earned a BA in applied mathematics from Harvard and a PhD in atmospheric science from the Georgia Institute of Technology, and served as a Fulbright Scholar to Australia. He's a recipient of the National Science Foundation Career Award and the author of more than 50 peer-reviewed publications. His recent book, Confronting Climate Gridlock, How Diplomacy, Technology, and Policy Can Unlock a Clean Energy Future, was published by Yale University Press in 2022. So after this discussion, we'll have a Q&A session, or please submit your questions. Do it through the Q&A and not the chat. And meanwhile, I'll transition the screen sharing over to Daniel. Thank you.
Okay, my slides showing okay?
Yeah, I see it.
Yeah, well, it's a pleasure to be here and an honor to be in that lineup of speakers. For those who may be here just for this talk, definitely encourage you to go to those next two. I had the pleasure of hosting Dr. Azevedo a few years ago for a seminar at Rice that was truly outstanding. And she actually advised one of my former undergrads when he did his PhD, and then John Berger with Sonova, really innovative company, and they've been a mentor for my class. So it's an honor to be part of this lineup that UT is putting together. Honored to be able to speak, even if virtually, to University of Texas from here at Rice, the private school down the road, but actually have parents who met at University of Texas, a brother who went there for law school, a brother-in-law who teaches architecture there. So really love the opportunity to speak to a UT audience and an audience from wherever you may be tuning in from. So this is a chance to talk about my book that just came out a couple weeks ago, published by Yale University Press at the end of March, and a book that looks, as you can see from the title, at three dimensions: diplomacy, technology, and policy. But being a UT Energy Symposium, we'll focus on the technology here. So David already gave the background, and those who want to see more, I have a website there that tells more about work that I do, as well as the graduate and undergraduate students in our group. And the book is available now anywhere that you want to get it, whether online, the hardcover, it's on the ebook, and was very fortunate to have it produced by a professional audiobook producer with Ray Greenlee as the narrator. So encourage people to check it out and follow up afterwards. Happy to hear any feedback that you might have. So if you get it, this is what you'll see on the title page. First of all, you'll notice at the top that greatly appreciate Michael Weber writing the foreword for this. Professor Weber's been a longtime colleague and collaborator, and really appreciate that he took the time to do that as the author of two successful books himself. You see that sort of after introducing the problem, the book goes through two chapters on diplomacy, both the history of how we got to the international situation we're in today, and some ideas both within the Paris Agreement and drawing on game theory, drawing on international relations scholarship, drawing on a wide range of ideas of what could be done both within the Paris Agreement framework and other ideas, climate clubs, technology initiatives, other things that could be done in the international arena. What I'll be focusing on here is really the heart of the book, being an atmospheric scientist, being a professor of environmental engineering. Over half the book is really devoted to technology that I'll be focusing on here arguing that there are some central pillars on which clean energy must be built, and then have a policy chapter that ties it together. I'm an atmospheric scientist, teach environmental engineering, have been at Rice for 16 years now. So there's a lot of this that I could have written off the top of my head, but this is something where I really drew on my background as a journalist with high school and college newspapers and with the Dallas Morning News science section. And so really went back and instead of writing the way you'll see some books on these topics is really, saying the author's own perspectives and expertise. It's really a sort of blended of the science and the expertise of over 100 people who graciously took the time for interviews, all walks of life, all areas of expertise on confronting climate change. So these three keys, and I'll be focusing on the technology key today, but just to show how it's laid out, and the reason for focusing on these in the book is because diplomacy and policy really depend on each other. Is that without diplomacy, there wouldn't be as much of a pulse of being impelled to act, of a way to leverage whatever we do with our policy to get others to come along too, especially as a country whose emissions had been tops in the world, but have declined to only be about 1/7 of the world's emissions. But we need policy to drive diplomacy, because if we aren't acting domestically, then we don't have the clout and credibility needed to push things in the international arena. Diplomacy and technology are intricately interrelated, because diplomacy is needed to have the collaboration for technology. We're talking about needs to either invent and innovate new technologies or deploy and improve and bring down the cost of technologies that already exist. All of that requires operating at scales that go beyond any one country's borders. And technology allows diplomacy to do more. So when we're aiming for Paris Agreement targets of temperature, we're aiming for reaching net zero, whether that's even viable for diplomacy to seek depends on how technologies develop, improve, and come down in cost and improve in affordability. And then technology and policy are interrelated. So I'm someone who actually, out of my PhD at Georgia Tech, went to the policy arena for a couple of years. I was at Georgia's Environmental Protection Division, their state's equivalent to TCEQ, where we were developing the mercury policy for the state. We were developing the regional haze plan, the ozone and PM 2.5 plans, and realized this interaction between technology and policy is that as we were writing those state rules, it was really the technologies that enabled us to pursue more ambitious policies, as you see on the upper right. And sometimes we pushed things. We pushed regulation before all of the best possible mercury controls were out there. And we knew, if you regulate it, they will come. If we put in those standards, that it would require innovation to meet those standards that were put in place. So this is a book about confronting climate gridlock, and really emphasize the confronting, and emphasize that this is a book about solutions. I had to push back against the editorial board when I had written everything and framed it around that title, and the editorial, the set of editors at Yale University Press came back and said, hey, how about we save a few drops of ink and save a word and just call it climate gridlock? And I said, no, absolutely not. This isn't a book about the problem. This is a book about the solutions, but we need to understand the problem that we're facing. And the problem is that we are on a very quickly warming planet, where if we go from a baseline of the late 1800s, when we first had a good enough, broad enough thermometer network to be able to more clearly determine what the baseline temperatures were, we've warmed up by about 1.1 or 1.2 degrees Celsius, by more than 2 degrees Fahrenheit already. And this is a global average. So over land, it's warmed up much more than that. Land is warming faster than the ocean. The Arctic, Alaska are warming especially fast. And linear extrapolation isn't necessarily how temperatures will go, but just with that simplistic approach, you'll see that the Paris Agreement targets that we were aiming for, the Paris Agreement said we would try to hold warming below 1.5 Celsius. We could hit that very likely within the 2030s. And we said we would hold warming well below 2 degrees Celsius, well, not well below 2, but we could be past 2 by 2060. or so. So it's urgent that we act on this quickly, and we're not going to hold in these temperatures until we can rapidly reduce emissions and move towards not just having emissions peak, but steeply reduce and be on a pathway towards net zero. They have not been on that pathway towards net zero. Instead, emissions have relentlessly gone up worldwide, with just brief interludes when the communist countries collapsed, when there was the 2008 global financial crisis with the COVID pandemic. But after each of those little dips, we've gone right back to record amounts of emissions. And so right now we're at a point where, as a planet, human emissions just from fossil fuels are over 36 billion metric tons per year. In other words, nearly 5 metric tons, or well over 10,000 pounds per person per year. So we're emitting many, many times our body weight, tens of times in fossil fuel emissions, not because of what we breathe out, that's part of a natural cycle with the food that we eat, but because of burning fossil fuels. And in fact, we emit more than the weight of the fossil fuels we burn, because all the carbon that's in those fuels picks up 2 oxygen molecules from the air and becomes CO2 that is rapidly warming our planet. In terms of where it's coming from, it could be argued, and I think the toughest question that I got in getting the contract from Yale and getting offers from other publishers was why write a book mainly focusing on the United States when the United States emissions have already peaked. For a long time, we had the highest emissions in the world. The US is that sort of green curve there. And around the turn of the century, all of a sudden, China started industrializing its economy at scales that hadn't been seen before, mostly on the back of coal, and far surpasses the United States overall. The United States is still by far the leading emitter per capita of any major economy. And so the US has fallen to roughly 14%, or a little less than roughly a seventh of all emissions. So if we control only ourselves, we aren't doing enough. But clearly, we're big enough, being second to China, being so big per capita, that we're going to have to be part of any solution that helps bring the world closer to a net zero future. We are extremely high. If you look, we're the top of any of the major economies in terms of per person. Americans are emitting an average of more than 14 tons per year from their fossil fuel emissions alone, and we need to be on a very different path. As a world, we need to be on a path that looks like this green or this light blue curve if we want to be in the 1.5 to 1.8 or 2 degree horizon. This is the one thing that has changed since I finalized proofs of the book, is that finally we've gotten to a point where the pledges are almost enough to get to our goals. So the pledges, the light blue line that you see here, that largely reflects the pledges that President Biden made of getting the US to over 50% emission reduction by 2030 from a 2005 peak, getting the United States to net zero by 2050. China pledged carbon neutrality by 2060. European Union, I think, is 2050 for their net zero pledge. So if countries really did follow the net zero pledges that they've put forward, it would now be almost enough, be within spitting distance, be within uncertainty range of getting to the temperature range we're trying for. 2 degrees, 2.1 degrees Celsius would be emissions that have been forever going up, would be on this light blue curve. We need to do a little bit better if we want to truly be well below 2 degrees. Unfortunately, this broad blue spectrum at the top shows where we actually are. So there's been a lot of hot air so far. There's been pledges from President Biden, from President Xi, from others, where they're saying they're going to go carbon neutral. They're saying they're going to go net zero, but the policies don't add up. There's nothing coming through Congress, coming through the Chinese Communist Party, whoever the decision makers are, haven't actually passed policies to get us onto these curves. And so we're in a case where if you just look at policies that are on the books, if you just look at what's actually been mandated, what's actually been regulated, we're probably on pace to have half to a degree Celsius or well over a degree Fahrenheit more global warming than was intended. And because emissions would stay, in this order of emissions being over 30 billion tons a year, even out to 2100, that wouldn't be where temperatures would stop, but temperatures would keep rising and rising throughout the 2100s at the pace we're on. So this is not a pace that we want to be on. It's not a pace that the world, that 197 countries all signed on at the Paris Agreement saying we would slow down warming far more than that. It's also not a worst case. You'll maybe see some gloom and doom scenarios. Sometimes they're based on the code for it is RCP 8.5. We're not on those scenarios anymore where there used to be projections that just showed emissions going up and up as far as the eye could see. Coal doubling or tripling from the amount that we're using each year. Today, I don't think we're on those worst case scenarios anymore. I don't think we're at risk of warming 4 degrees Celsius by the end of the century, but I would much rather be on these curves that hold warming to 2 degrees Celsius or less. So how do we get there? Well, we're not going to get there by the United States alone. This is something that I do as an exercise with my students. It's a online tool that's built around an MIT climate model. And what I did here is the way that this model is set up that I often step through with my students is it puts emissions by year by each part of the world. The red curve is the United States. And in their model, I think they're pretty pessimistic, thinking that the US emissions without any policy would just stay flat and then it would start ticking up after 2050, just as the economy and population grow. In the bottom curve, I hypothetically said, well, what if we really follow President Biden's initiative and we aim to get pretty close to net zero by 2050? Well, in their model, I think their model is overly pessimistic for the US and for other countries. So their model puts us warmer than I think we're possibly going to get at 3.6. But my point here is that even if Biden succeeds, even if we switch to net zero in the United States, we would only avert 0.2 of a degree Celsius of warming. I shouldn't say only 0.2 of a degree Celsius is actually a large amount. Prehistorically, before the industrial era, it usually took at least a couple of centuries for the world to warm by a couple tenths of a degree Celsius. And that would be when we were naturally rocketing out of an ice age. So that's 0.2 is a lot. But if we need to get a degree of cooling or a degree less of warming than our status quo, what the US does is part of the solution. It's necessary, but it's not sufficient. And so we need to not only decarbonize the United States, but we need to show that it can be done affordably, so that it's affordable not just for us as the wealthiest country on earth, but for other countries that would want to decarbonize as well. We need to show it's reliable. So we can't be in the situation like how the electric grid failed us in 2021 with the mostly fossil fuel grid that we had. We need to show that a cleaner, decarbonized future can even be more reliable electricity, more resilient electricity and other energy. And we need to get there fast. We can't wait till 2100 to get there because we have more wealth. We have more opportunities to develop and demonstrate these technologies. So if we want the rest of the world to bend its curves, and especially bend that biggest emission curve that is other developing countries, the other developing other than India, the Africa and Latin America and Southeast Asian countries where most emissions are expected to happen, we need to achieve decarbonization of the US in a way that makes the rest of the world want to follow suit. So that makes the US crucial. We've had the largest amount of emissions of any country historically. And so a lot of the CO2 that's in the air today is what the US emitted over the past 2 centuries. We're tops per capita. We're the largest economy and largest consumer market, which means that what happens here is going to drive the manufacturing decisions, drive other decisions that are made in other countries. We're the leader in technology development. So China has pretty much caught pace in terms of papers and other means, but really nowhere else has the system of top-notch universities, of Department of Energy national labs, of some things that come through Department of Defense, of just the range of both private and public sector technology development, the venture capital community that's able to fund some of those efforts, that's able to cross those quote unquote valleys of death and bring technology from the lab to the market. The US is really second to none. In that, we've been both the leading driver and the leading barrier to diplomacy. And we need to make this succeed here, cheaply, affordably, reliably, resiliently, to make this viable everywhere else. So focusing on the technology key, I can pause now if there are any questions about this framing before we delve in to the solution. So I don't know if David, let me know if any questions have been posted into the Q&A. I think we're using the Q&A for questions. So I'll just pause for a moment if anyone had a question about this framing of the problem before we jump into, okay, how do we do this? How does the US push the technologies forward to make this happen?
Thanks for pausing. No questions yet.
Okay. So the challenge in finding solutions, and if you look at the writings of Václav Smil, for example, who's been very influential on Bill Gates and others cite him a lot. Scholars who've looked at energy transitions historically tend to be pretty pessimistic because they argue that if you just look overall at the overall, what is the top fuel that's fueling the economy, usually we're talking 50 to 100-year transitions to really turn things around. That we were mostly renewable energy economy for our first century as a nation. We were mostly wood era. That yellow curve, the biomass curve, was that we mostly burned wood and used a bit of hydropower for almost everything that we did. Only around the time of the Civil War and then on into the late 1800s, early 1900s, did coal really come to the fore? That if we wanted a more energy dense source for our railroads, for our steamships, for being able to power larger scale industrial operations, wood didn't get hot enough, wood didn't have the energy density, and so we switched to this coal era. So essentially we carbonized our economy before we aimed to decarbonize it. Now, and then, long after Spindletop and other developments brought oil and gas into more widespread use, and those who've read Daniel Yergin know that he really brought to life this transition of how oil came to the fore, really took until after World War II, until we were mostly an oil and natural gas economy, with those overtaking coal, and is really the economy that we're in today. And so how do we have a transition where the renewables that are chugging up from that green curve, how do we get to the point where they're not just growing, but where they're far beyond and allowing petroleum, gas, and coal all to decline so that we can be in a decarbonized future? If we look at the projections that the Department of Energy put out last month of where they think we're heading, yes, they think that renewables will go up. This is a bit more updated than the slide before, but you see it still shows renewables staying behind natural gas and behind oil in terms of production, shows coal declining, but still remaining too much coal, that gray curve heading into the future. So a curve that really leaves us emitting just about as much carbon dioxide as we do today, not getting us to the net zero by 2050, but a future that really doesn't get us off oil or gas at all and only marginally has coal go down. So this, without having policy, without taking action, we're not where we want to be. Yes, there are problems with these outlooks. I've written a number of articles about problems with the outlooks, but still, to the extent that they're valid, we need to be on a much, much better path than what EIA shows. Where there's hope is that if you look beyond just all oil, all natural gas, all coal, but you look at specific technologies, often these get adopted with very, very fast technology adoption curves. If you look at how quickly automobiles got adopted, you look at New York streets in the turn of the century, right at the start of the beginning of the 1900s, all you would see was cars and horse and buggy, carriages, horse and buggy carriages. Within 20 years' time, you hardly saw any horses. It was all cars on the road. We picked up black and white TVs incredibly quickly, where they became ubiquitous in American homes. And then within a decade, replaced them with color TVs as those became more available. VCRs, cell phones, all these technologies, once they've become available, once they've become better than the alternative, we have these S curves where we have this slow adoption at first. And then once you get past that 5 or 10% adoption, they can often just rocket up to being ubiquitous, to being in the vast majority of US homes. So can we be in situations like that. So that's one reason for optimism. Another reason for optimism is that the outlooks, the annual energy outlooks that the government puts out each year from the Energy Information Administration have been terrible in the past. Is that coal had been on this ever upward march and then kind of plateaued. And then each year when they issued their new outlook of what coal would do, they predicted basically that coal would stay flat. Even as coal declined, they would issue a new outlook saying it would stay flat. Reality is that the coal use has been much less than what they forecast each time. So I don't think the future will be as dirty or as coal heavy as EIA thinks, but still we're not where we need to be. We need to be virtually completely off of coal in this country if we have a hope at net zero. The other thing that gives hope is that forecasters, EIA looks like this, but here this shows that the International Energy Agency, the IEA, is having problems with its forecast too, is that year after year solar grows and they issue another forecast just flatlining how much solar they think will happen. They've started now to predict a little bit of upward trend, but again, actual 2021 is already more than what 2019 forecast we would get to in 2040. So it's just been rocketing upward year after year, much faster than any of these forecasters had thought possible. And the reason why we're installing solar and installing wind, and I think soon we'll be installing batteries faster than had been thought possible, is because costs have been on this incredible cost decline curves. Is that back in 2010, a few years after I began teaching at Rice, the cost of solar was still on the order of 25, 30 cents a kilowatt hour. And the projections were, if you looked at, say in 2010, IEA's projections were that solar was going to stay sort of asymptotically approach 12 or so cents a kilowatt hour out until 2050. They knew the technology would improve, but they thought we would still be 12 cents. They issued later forecast, came down to 6 cents. Ramez Nam is a futurist who used to be laughed at as being wildly optimistic in his forecasts, thinking that we might get down below 5 cents by the 2030s. Instead, we're down at 4, or most estimates I see now are in the 3 to 4 cent range for solar right in 2020. So lower than even optimistic futurists thought we would be 15 years from now. It's been happening so fast, essentially because of learning by doing, because with each doubling of deployment, and we see this in solar each time that more and more has been done, is that the costs keep relentlessly coming down. Enjoyed speaking to Jessica Transick for the book, a scholar at MIT who's been studying these curves. I also spoke with Greg Nemeth, a University of Wisconsin professor who wrote the book, How Did Solar Become Cheap? And they find these trends that for each doubling in cumulative deployment that's happening, the cost has come down by about 18%. You come down enough 18%, time after time, you bring the cost down to where they are today, where they're down probably in the 30 or so dollars per megawatt hour at sunny sites. So it's become the cheapest form of electricity where it hadn't been expected to be that way if you look at forecasts that were issued just a little while ago. So this relentless, this learning by doing, this technological development, and it means that if you missed the deployment, if you missed how fast the cost would come down, that you wouldn't think we would deploy as much, which means you would miss the forecast of how much cost would come down. And it's this virtuous cycle that feeds on itself. It makes for terrible forecasts. It means that the forecasts keep getting it wrong, but it's great for being able to push forward clean energy, because it's really been the rocket fuel that's been able to propel us to much cleaner and much more to much cheaper and much more widely deployed solar energy. And this isn't something unique to solar. This is a plot that shows what Model Ts cost when Model Ts were being introduced. The more and more that Ford built more Model Ts, those also went on a similar curve, as with each doubling, the costs came down that same 18 or 20 or so percent. This isn't a law of nature. This isn't something that absolutely must happen. The costs of solar have ticked up over the past year as we've had the supply chain problems, as labor, as cargo ships, as every imaginable metal and material needed for them has gone up. So I think it's probably a temporary uptick in prices, just like, what is it, Moore's law that says that computer chips keep getting faster and more powerful and cheaper. There's no guarantee, but if you look over this over time, you wouldn't want to bet against this ongoing trend of manufacturers just keep getting better and better. Also have optimism because of visits that I did to NREL and other places, meeting developers of technologies like solar perovskites, like organic solar, like quantum dots, other technologies that if silicon cells ever do cease on their curve, there are other technologies that could step in and potentially bring down costs even further. So what steps do we need to realize this? Well, this is a curve that was put forward at the end of the Obama administration. It was issued the second week of November 2016. Didn't get much attention because by the second week of 2016, the President Hillary Clinton administration that I think the Obama White House thought they were planning this for wasn't going to exist, and the world was focused on Trump's surprise election, and Trump quickly removed this this report from the White House website as soon, I think within a day of taking office. But what was thought at the time was that if we started from 2005 emissions levels and we only let the economy and population grow and have other change happen, we would start at this problem of the United States being at 10 billion tons per year of greenhouse gas emissions. 10 billion tons a year of CO2 equivalents is what the business as usual would be in 2050. And so they showed this waterfall of what could get us to where we need to be. This three-part, really three pillars of clean energy that we need: efficiency in transportation, in buildings and industry. We need clean electricity, which is actually the biggest decline because at the time, power plants were still the largest emission sector. They've been overtaken by transportation, but if we're going to clean up transportation, we're going to need electric cars. We're going to need more electricity than we generate now. So actually the biggest pillar in what electrification rides on is by moving to clean electricity. And we need to electrify. So we need to electrify as much as we can. So switch from gasoline and diesel vehicles to electric, switch from natural gas and propane heating to electric heat pumps. But there are things that we can't electrify, so we'll need low carbon fuels for those, for planes, for ships, for certain industrial processes. And then outside of the energy arena, we need land to pick up land sinks. We need some sort of CO2 removal technology, which actually even itself depends on getting electricity to be clean and cheap, because most strategies for CO2 removal actually are hugely energy intensive. And then we need to clean up other greenhouse gases: methane, nitrous oxide, fluorine gases. My group has done a range of research on natural gas flaring, have done research on nitrous oxide emissions from soil, so happy to talk offline about any of that. And then President Biden came along and said, well, President Obama's goal wasn't good enough. He doesn't want to just be at the 80% reduction that President Obama's White House aimed for. President Biden's target is to get to net zero, so we're going to even need to do better than all these downward arrows would suggest. Another great way of framing this challenge, if we frame it as needing those pillars, those three central pillars for clean energy and the two other pillars that we must do, we can also think of it in terms of how the energy economy is powered today, is that we have these four main reasons why we use energy in the United States, or really this is for the US, but you could make similar boxes for any country on Earth, is that we use it for transportation, we use it for industry, for residential, meaning our homes, and for commercial, meaning our buildings. And I like the way that NREL made this curve because they show this electric frontier. They show this heavy black line is that everything below the black line is powered with electricity. So you'll see lighting, refrigeration, air conditioning, certain industrial operations, all those just inherently electricity is already powering those. So if we can move to be more efficient, then we'll need less electricity. Efficiency will shrink all of these boxes. And if we clean up electricity, we can clean up basically everything that's being emitted by power plants in order to power this area below the electric frontier. All of that can be cleaned up with clean electricity. Electrification is a matter of moving up this frontier. As we get to cleaner electricity, it's going to make more and more sense to see, can we move this up and use that clean electricity for other things? Can we use it to power biggest box of all, the light duty vehicles? Can we use it for freight trucks? Can we use it for certain industrial processes? And then both space heating and water heating are the main ways that buildings still burn natural gas and burn propane and burn heating oil. Can those heating of homes and businesses be switched to be electrified? And then we'll need clean fuels for what can't be electrified. And we're not going to completely eliminate all these boxes or their emissions equivalent. So how do we offset the rest? When it comes to that central pillar of decarbonizing electricity, you'll hear debates, you'll hear the tribalism of it needs to be nuclear, it needs to be solar, it needs to be geothermal or wind. As far as the climate is concerned, who cares? They are all incredibly clean compared to any of the fossil fuels. These three dark blue areas on the right are the ones of fossil fuels. The orange shows that even with carbon capture, which hasn't been done in any widespread commercial scale, would still be more emissions than any of the cleaner options. So anything we can get to in this red box, we're all on the same team when it comes to nuclear or renewable energy are all clean, but they don't look the same on a cost basis. So what's winning the race by far is solar photovoltaics and wind. This is on an unsubsidized basis. So this is before even counting the tax credits that favor solar, wind, geothermal, and nuclear, is that they're just winning the race on cost. By far cheaper than anything else. What these diamonds show is the cost of just running an existing nuclear or coal or combined cycle gas plant. I think this is before gas prices had their recent surge past $7 a million BTU. So they're competitive with existing fossil and nuclear power plants. They blow away are far less than the cost of building a new nuclear, coal, or gas plant. You see offshore wind is this diamond here. So offshore wind is still costly, but it's getting close enough to these boxes that it can make sense in places like the New England and New York, where there's not much cheap land and offshore wind can power those big cities there. You're seeing geothermal getting close to that range, where because geothermal is able to generate at times when wind and solar can't, that it's becoming more appealing, and it's getting close enough that it could start hitting those learning by doing cost curves, or with some subsidies, geothermal could be in the range. Unfortunately, especially after the failures of South Carolina's nuclear, of Georgia going $15 billion over budget, nuclear is not cost competitive anytime soon. It's because of these relentless cost declines. Solar costs have come down 90%, wind costs have come down 72%. So if you looked at costs a decade ago, you would miss where the market is today. Coal and nuclear have gotten more expensive over that time. Wind and solar have gotten less expensive. And we're starting to see the same learning by doing. This technology cost curves are kicking in for lithium ion batteries as well, where they've been going through the same sorts of curves of percent reductions as we've had each added deployment of batteries, whether it be batteries for cars and buses and trucks or batteries for the grid. As a result of these very fast changes, because solar and wind and batteries have become far cheaper than was imagined a decade ago, and nuclear has become more expensive, and carbon capture really hasn't panned out so far. It's already been turned off at the only place in the United States that tried to do carbon capture on coal. So when I talked to Jim Williams, who developed this project, and notice I underlined this is 2014, this is not what he would do today, but this was basically modeling done a decade ago that got reported on in 2014. When he was looking at the situation, he was part of a decarbonization pathways project. And his study showed that there were three scenarios of high renewables in this line, a high nuclear, mostly nuclear electricity, or a mostly carbon capture and storage scenario. He thought they were all about equally likely. He thought the nuclear scenario was the least cost scenario. He did a mixed portfolio of them too. To him and to this report and the team that developed this for the United States and other countries, a decade ago, they thought that any of these were really viable of what the electricity mix might come from. If you look at anything new that's been issued recently, for example, Jesse Jenkins and Stephen Pakala and others issued this as this Princeton study. What you see is just mostly blues and yellows, is that all the scenarios now that look at costs and look at the cost curves and where things are heading have almost all the power, all the electricity growth in the future coming from wind and solar. So there can be merit for keeping existing nuclear, merit for keeping our existing hydroelectric dams. But unless they do this weird scenario, this RE minus, where they just artificially constrained wind and solar to not grow any faster than they have in the past decade, everything else besides just this artificially constrained one you see is dominated by wind and solar. And Jim Williams, when he's gone back and done his own analysis and modeling, when you look at the net zero project, all of the modeling that looks at recent prices is all showing wind and solar dominant, and it's a question of what else will balance that. That's going to come with a lot of land use. So the blue shows in these various scenarios how much land would be within range where you could see a wind turbine from where you are. And so you would have, not that you would put it in these light blue states exactly, but it's a sizable amount of land that would need to be within viewing range of a wind turbine. The square shows that the turbines don't actually take up much space. We're going to need to be smart about co-locating turbines with grazing, with farming, with other purposes. The yellow shows how much land would be taken up with solar panels, which aren't as easy to co-locate or use land with other things. The green shows if we go to a lot of biofuels, that we would need a lot of land for that. Over the course of researching the book, I became much more hopeful about geothermal, interviewing a number of people in that industry and had the exciting opportunity to follow a developer from the point where he was fresh out of business school. He was just in a clean tech incubator program at Berkeley National Lab, and he graciously hosted me during my sabbatical. I spent a couple weeks in Colorado, a couple trips to California, and went to Berkeley National Lab to see about a dozen or so people like him who were just had ideas that they had developed in grad school, had developed in their PhDs, and developed in their MBAs, didn't know how to take it to market, and it was this 2-year incubator program. Well, by the time I was done with the book, these are headlines that they're generating, is that they've been tapped for tens of millions of dollars deal from Google because Google, Microsoft, others are committing to 24/7 around-the-clock clean electricity that they can't get from wind and solar alone. And so they're getting these big deals, Criterion, Evor, Deep Energy, all these companies that barely existed when I started researching the book in 2017, 2018 are now coming to the point of nearing market stage. So once we make electricity clean, we're going to need to electrify. We're going to need to push up that electric frontier. That's going to mean largely changing the way we heat our homes. So here in Texas, 60% of our heating is already electric, but we saw the problem of inefficient heating is that much of that electricity is resistance heating. It's basically like a big toaster oven or hair dryer that we use to heat our homes. That's very wasteful of electricity. Or it's heat pumps that have resistance backup. So those are much more efficient day to day, but when it comes to a deep freeze, they become huge consumers of electricity. So we need heat pumps, and we need better heat pumps to replace electricity and natural gas. We need other parts of the country that are still using fuel oil, kerosene, propane, and natural gas are going to need to switch to heat pumps and switch to better heat pumps and more affordable heat pumps than what's happened so far. That, the space heating, the water heating are the biggest home and business users of fossil fuels. And you see all the scenarios. This is a different one, a zero carbon action plan. Found some very similar results to what the Princeton study was showing. Just like they agree that we need mostly wind and solar balanced with other things for the future grid, just about all these studies come to this conclusion that we need to be switching to heat pumps to be using that clean electricity to heat our rooms and our water. So how do we get there? Well, what gives me hope that we can get there is because we need to be able to hit these virtuous cycles of learning by doing, these technology learning curves, where things that look a little bit too costly now, once you start producing them more, once you start deploying them more, their costs can come down, which encourages more people to produce and deploy them, and then we keep going in this virtuous cycle. And so what policy, without going through the full details of the policies and the politics and the public opinion and other things that I go through in that chapter, a key take-home message is that we need policies that do two things. And I came out somewhat agnostic. I talked to people who are pushing the carbon tax, like talking to Secretary of State James Baker, who wants a carbon fee and dividend. The Climate Leadership Council and the Citizens Climate Lobbies director spoke to me. Great rationale for a carbon tax. Others have great rationale for industrial policy, or great rationale for mandates or regulations or other approaches, R&D boosts. To me, where I came out is we need policies, however they're designed, whatever the flavor, we need policies that can pass. They don't have to be perfect, but they need to accomplish two things. First, we need a push. We need a push of technologies that make there be more of a supply of technologies that don't exist now, or that exist but haven't been demonstrated at commercial and larger scales than the pilot projects. And so we need a huge boost in research and development funding. And then with that push, we need a pull. We need a market pull of policies that make sure there's a demand even before these technologies have become as affordable as their fossil competitors. Those things that create demand can be really crucial. So the procurement, what Greg Nimitz was showing in his book, How Solar Became Cheap, is that because there were governments, commercial, other companies and consumers that decided to deploy solar even before it was cost effective, because you have government fleets that might choose to buy electric cars. For example, why that's so important for the Postal Service to move to procuring cleaner vehicles is because it creates that market that pulls us along this learning by doing curves. It can come by incentives, it can come by mandates, it can come from the carbon taxes or fee and dividend that others propose. Whatever we want, we need to create this virtuous cycle of pushes and pulls. So some take-home messages, and I hope start putting your questions into the Q&A box now, but just to summarize some of the key messages from this is that I would argue that decarbonizing the United States is a necessary but not sufficient action that must be taken if we're going to decarbonize globally. There are these three central pillars on which clean energy is going to have to be built: efficiency, clean electricity, and electrification. I do devote an additional chapter of the book to the carbon offsets, to the ways with natural approaches, with direct air capture, with weatherization approaches of how we can offset what's left. But the main thing we need to do is we need to cut emissions 90% or so by these three central pillars: the electricity, the efficiency, the electrification. Solar, wind, electric vehicles, perhaps geothermal, if it's able to hit those curves that I think it might, and heat pumps are likely to be pivotal to leading the way. And we can discuss and disagree and have political look at things of what's the best push and pull policy, but one way or another, we need those pushes and pulls to get us along this virtuous cycle, this learning by doing that gets me hopeful that we can pull these technologies forward and that we can truly confront climate gridlock, not just in the United States, but in a way that can become a model and can help propel efforts like this around the world. So appreciate you taking the time for this. Hope many of you will choose to read the book and come back with questions later as you do so. But I think we have, 12 minutes or so for whatever questions are brought up in the Q&A and any other questions that might be raised.
Fantastic. Thank you so much. Excellent. Here's the first question. What do you say to industry and their risk assessment models to encourage investment in technologies that do not immediately appear to be cost competitive?
Yeah, the industries that are willing to invest in technologies that aren't quite cost competitive are unbelievably powerful, will have unbelievable leverage in driving things forward. I mean, I think the example that I showed with what's driving geothermal forward, where it's been virtually dead. It's been 0.5%. It's only been deployable where you have steam virtually coming out of the surface. What's bringing it forward? What's making it one of the hottest areas of energy is because companies like Google, like Microsoft, have been willing to say, okay, you cost twice as much as wind and solar, but we're just going to make it our internal policy to get 24/7 round the clock in region energy. And yeah, you shouldn't be willing to pay 10 times as much. You'll push yourself out of business. But those companies that are willing to say, we have this commitment to 24/7 clean electricity, or we'll put an internal carbon price, we'll penalize ourselves internally in our decision-making $20, $50, $100 a ton for the emissions that we make. We have a pledge of getting to net zero internally. Those kind of buyers who aren't pushing themselves out of business, but who are making a market for things where it's close enough to be driven forward, those companies, those government agencies, those even individual purchasers of electric cars that may be not quite there, that really gets us to the point where the market can take over from there, where even companies that aren't choosing to do this are just going to do it because it's cheaper. But we need those early adopters. We need to get up those S curves with that rapid deployment at first.
Very good. Another question, can the switch to greater efficiency, zero carbon generation and electrification be done in a way that actually reduces customer electricity bills, or at least keeps them from increasing?
I think so. I think if we do this right, and the modeling bears this out, the modeling by Princeton, the modeling by Jim Williams' group, the modeling by the Net Zero America, all of them show costs of electricity being roughly the same or slightly lower if we go to a near net zero or 90% clean electricity than if we stuck with the status quo. So I think most likely the cost would be about the same or a little bit lower because we'll avoid the fuel costs. Better yet, we will have a lot more certainty and predictability. Natural gas prices were $2.50 a million BTU. Now they're over $7.50. And that's in the US. Other parts of the world are facing much higher natural gas prices with wind, with solar, with transmission lines, with geothermal. We know what the cost will be roughly upfront going in. We aren't left with those shocks of spikes in prices, of the natural gas system failures that we had in 2021. If we plan for it right, if we plan for it with an adequate blending of complementary resources, and we build out the transmission to be sure we can access the windiest and sunniest and best geothermal locations and blend it with existing hydro and nuclear, then I'm confident that we can get the cost of electricity down, and we need to, because if we only do this expensively, if we do this mostly with nuclear that's costing 5 times as much, yes, nuclear is clean, but why would we electrify cars? Why would we electrify heat pumps if we're going with things too expensive? So I not only am hopeful that we'll keep the cost the same or go down, but I'm counting on that to make electrification make sense.
Okay, next question. Do you see a role for clean hydrogen produced by electrolyzing water? I guess that could be either green itself or blue with CCS.
Mm-hmm. Yeah, I would say that is one where that was one of the biggest wildcards that I think remained agnostic after listening to experts, really brilliant people on different sides of the issue that had factor of 10 different projections of where we'll be for hydrogen and different projections of how quickly we can move to the green electrolysis approach. Having looked at methane leaks, having looked at other things, if we really want to go low carbon, we have to go the green way eventually, even if blue is making it from natural gas with carbon capture might be a bridge. Big uncertainty, I think, is in the heavy duty freight or the local freights and delivery transportation. Will we start to see hydrogen be used there? If we see it used more in industry, then it could be big. I'm a bit skeptical about the idea of long-term storage with hydrogen, although it's certainly possible, but the energetics are terrible for that. I think DOE now has its hydrogen shot goal of aiming for $1 a kilogram green hydrogen. I don't think they're on the path for it yet, but if they can get there by the early 2030s, that's going to be transformational. If we really can get to $1 a kilogram, just like it seemed impossibly ambitious when they aimed for $1 a watt solar, that hydrogen shot initiative is could be a game changer, or we could stumble, and we're going to need hydrogen for fertilizers, for chemicals, for ammonia, for other things. But there's factor of 10 difference depending on how well we meet those targets in the decade ahead.
Mhm. We've got a number more coming in now. Why do you think the government funding for geothermal energy, despite having a lower LCOE, is far lower than, say, nuclear energy, when it seems like it could have a much greater impact in the near term?
Yeah, I mean, nuclear is starting, 20 times more than geothermal is. Geothermal has been stagnant for a few decades. But yeah, if I was to bet, I wouldn't count on anything that's so small picking up, but I just don't see a path to much nuclear being added in 10 years. New nuclear, small modular nuclear has been 8 years away for the past 10 years or so. And it's just not at a point where if we're really aiming, as President Biden is, to get mostly clean electricity on the grid by 2035, geothermal is something that can be modular, that can be deployed again and again, really the way fracking is. And so I think, the nuclear industry is bigger. The nuclear has more lobbyists, has more history to it. It has the need because of the nuclear weapons and the waste. But yeah, it's going to be crucial to fund geothermal with things like the Forge project. We probably need a couple more sites like Forge to really test out these technologies. And I'm hopeful that those early adopters can, the Googles and others can drive that forward.
Okay, next question. Thoughts on EU and Canadian CBAMs, that's carbon border adjustment mechanisms, to influence the US and spur us into action, despite our likely best effort to do the right thing only as a last resort?
Yeah, so I encourage you to look at chapter 3, where I really go into that in detail. But why I argue that the US is so important is when the US does something, we make sure everyone else does too. The Montreal Protocol for CFCs really came because we were already starting to ban some uses of CFCs. We didn't want to go it alone, and we forced everyone else to come with us. I think the European Union has for too long been making the mistake of being too nice to us, of saying they're going to do their own carbon taxes and carbon cap and trade system and not pushing it. Here, I think if we ever did a carbon tax, when I talked to Secretary of State Baker, his idea of carbon tax would come with a border adjustment. So we need either others to start getting as reciprocal as the US has been, or we need US to have policy that it has always wanted to be reciprocal. But yeah, having countries push each other forward with carbon clubs, with a lot of the ideas I talk about in chapter 3, I think has a lot of hope for propelling things forward.
Next question. What's the role of standardizing demand response DR to speed its adoption? I think all DR today is proprietary despite recent ANSI SCTE 267 2021 standards for optimal load shaping. What about standardizing DR?
Yeah, I mean, I think for demand response to happen, it needs to become automatic, at least at the home and commercial scale. It needs to be automated where you can override it if there's a change to your thermostat, but where things just automatically kick in. We need smart chargers for our electric cars. We need smart water heaters that decide automatically. If we're just counting on people making adjustments voluntarily, it just usually doesn't happen, except for maybe it does for audiences like us, the energy wonks, but at wide scale, it doesn't. Yeah, there needs to be dynamic pricing, demand response. A long way to go. And I think really, especially on the resilience and the reliability, to get through those dark and slow wind times, to get through the deepest freezes. We're going to need demand response to save us a lot of money so we don't have to so totally overbuild our supply and our storage side of the equation.
Okay, 2 more questions. The cost of distribution is an important fraction of both the cost and risk liability of the current electrical grid. Can you comment on the future of small scale, say household, block, neighborhood energy production and distribution?
Yeah, I mean, look, I've got solar on my rooftop that means that I can call it a solar car when I charge up in my garage. It powers about as much the full house's electricity net from solar. So I'm happy to have it. And to the extent that people have the right conditions and means to do it, it's great. And it can reduce some other burdens on transmission congestion. It's still much, much cheaper to do things at utility scale and do things with trackers. It's still, wind is something that you can't really do distributed. It takes so much more batteries to try to island things. there's a reason why civil engineers have called and others have called the electric grid the most important innovation of the 20th century, is because what it's enabled us to do by being all connected. There is so much value to that, and I wouldn't want to get away. There are purposes, there are needs of places that can't be on a grid or need to be islanded, and there is some resilience and backup there. But I wouldn't get away from what's good. I think we need to strengthen. I think we need to connect. I think we need to build a lot more high voltage transmission. And if we want to make things affordable, and if we want to make it equitable, where it's accessible by people who can't afford their own neighborhood or home or personal systems, I think we need to make the overall utility scale system better.
Mm-hmm. We're over time, but let me fit this one in. What do you think about offsetting carbon emissions? I think this question really is asking about direct air capture.
Yeah, so with anything, whether it's direct air capture, I don't think that the carbon sucking fans are necessarily going to win. There are other strategies, the weatherization, other approaches that might work. All of these are going to be expensive. So all these aren't going to play out without a policy push or something that makes them happen. We're talking over $250 a ton now for those engineered means. There's wishful thinking in some papers of how you could get it down to $100 a ton, but it only works if we make energy clean. It relies on natural gas with carbon, very, very efficient, very, very affordable carbon capture. And especially it relies on a huge amount of electricity. It's enormous amounts of wind and solar or geothermal or nuclear. Somehow you need to decarbonize the economy before you could even capture carbon in an efficient way, whether it's to run the fans and the chemical processes, whether it's to crush up the magnetite or the magnesium and calcium rich rocks for silicate or other weathering. Jennifer Wilcox, professor at Worcester Polytechnic, who got picked for Department of Energy, had a great way of putting it, saying that it takes about as much of an industry, as much stuff moving around and doing stuff to pull CO2 out of the atmosphere as it does to put it in there in the first place. And think about how big the coal, oil, and gas industries are today. So it's going to be huge. We need to shrink our emissions before it becomes even possible to offset. And we really need to make electricity and other energy clean first before anything else has a shot of soaking up the rest.
Okay. And I think we're over time here, but an excellent presentation. Thank you for your time and sharing your insights. And so let me finish by saying, please join us again next week on April 26th at the same time. Dr. Inés Azevedo will be discussing environmental justice, climate change, air pollution, and decisions in the U.S. power sector. So again, Daniel, thank you again.